reasoning models, like DeepSeek, O1. We've all been using them for different use cases, I'm sure, in production, in our day-to-day jobs. But they're great at problem solving, mathematical equations. They can show their work, help you follow along, see where the model was correct, see where it might have drifted off course, and gives you, it shows your work. I personally sometimes got docked on exams for not showing enough work, and these models, they show it for you. So that's great. They're also great at code gen and debugging. They're better at understanding the structure and intent of code. So you see them more, showing up as code pilots. So huge use case there that we're supporting. Um, and then due to their nature, they're more logical and they have multi-step reasoning. So unlike a traditional LLM that kind of just goes through the task at hand, start to finish, reasoning models, really kind of step back and explain their logic step by step, learn from themselves in action, um, and we start seeing more of those aha moments like we saw with DeepSeek. So that's why, we really like using them. They have some great use cases where they really shine. Um, but one of the downsides of using them is they're slow. Um, and by nature of being slow, if you're paying per GPU hour, they're also more expensive. So why are they slow? Here's a sample prompt that you might come in. Um, a quick question. Yeah, we'll email out the PowerPoint and a link to the slides and a link to the recording afterwards. Not to worry. So why are they slow? Here's an example prompt, very tight prompt. Here's an example of what part of the response could look like. So reasoning models, and this is, a fairly conservative example, but the reasoning models add this chain of thought visualization. So everything you see at that top part in between the think tags, um, they include the step-by-step reasoning behind their responses. So it's more tokens. So that just means more tokens come out, more tokens need to go through, and that takes more time. There's also more complexity required, in the forward pass per token. So the actual act of generating these tokens is also slower. So there are more tokens, and the process of generating each token is a bit slower. And again, it's a bit of that iterative process. So the model doesn't just kind of blast through the problem in one go. It does think iteratively, kind of reflect from its thinking and course correct live. So that also adds time, adds more tokens. So all of this turns into, just a bigger response that's going to take more time. And the downside of that is it often, kind of limits these models for being used in more time-sensitive live use cases. So it's harder to put these in production where quick responses are essential for your customer experience. So we're going to talk now about kind of how to overcome that challenge, and how you can actually accelerate these models so that you can put them into more of those kind of high, you know, real-time customer use cases. So Ajinkia told me that he was having a few issues with his camera that I'm not quite sure how to resolve right now, but I'm going to turn it over to Ajinkia. He is, one of our research ML engineers that has really been kind of at the bleeding edge of a lot of the work we've been doing on accelerating our models. So, Ajinkia, over to you. Thank you.
Thanks, sir. Thanks. So I'm going to share my screen. Uh, okay. Can you see my screen? Okay, great. Yeah. So as Will was saying, these reasoning models are great, right? Like they are really accurate. They provide their thinking, and they also, yeah. So But there, it comes with a downside, right? The downside is that you're generating so many tokens. So the question is, can you speed this up? Right? And so one technique to do this is what we have come up with is self distillation plus something called as Turbo LoRa, right? So the idea of self distillation is pretty simple. That you start off with a few prompts that you have, that the output of which you would like to speed up, and you start off with a LLM, like for instance Llama in this case, right? And it's frozen. It's you aren't tuning it yet, and then you forward a bunch of prompts through it, and you get some outputs, right? Once you have these outputs, you want to train something else, right? In this case, we call it turbos that help you go faster. And the way you go faster is by not just predicting the next token, which is what autoregressive models are in their basic native state, right? So you give some text and they produce the next token. You forward this token through the model again, and then you get a next token. So it's one token at a time. But instead of doing one token at a time, can we do three tokens at a time, right? If we could, then the inference would be three times faster, right? So that's the idea behind Turbo LoRa's. And the way you train them is you start off with some prompts, forward them through one LLM, get their output, and train the turbos so that you are able to predict the next token, not just the first token, right? And so that's the idea behind Turbo LoRa. And we have applied the idea of Turbo LoRa to other cases, and we have seen great results, right? So we thought, let's try them out in reasoning models where there is some repetition of the text, right? For instance, if you recall Will's example earlier, in this case, there is a bunch of double stars, there are a bunch of backslash and opening brackets, right? These are the things that you could easily predict. That, let's say you are at this, uh, you are at here less, right? Then you could that you are going to produce this particular thing, right? Then you, instead of just producing one backslash and then one square bracket, one token at a time, you could just produce those three tokens at the same time, and then you would see a speed up, right? So that's the idea. So that's the idea. Oh, sorry. Yeah. Oh, give me a second. Okay. So yeah, so that's the idea, right? And so let's see what happens when you do this. So for this particular application of Turbo LoRa, we chose the data set of GSM 8K, which is where the original DeepSeek carbon was showing really great improvements. And so by applying Turbo LoRa, the idea of self-distillation and Turbo LoRa, we were able to improve the throughput of DeepSeek digital Quen 32 billion parameter model from around 40 tokens per second to around 80 tokens per second. So that's twice the speed up. Now, we should keep in mind that the improvement that you get with LoRa is highly data set dependent. The improvement relies on the fact that if you're doing one token, that has a lot of information for the next few tokens. So you can take that token and predict the next tokens. This may not be the case with a lot of like some other data sets, but in this case, GSM 8K, it turns out to work well in some cases, right? So let's see a demo of how this works in practice, right? So we're going to skip the part where you actually create the distillation data set, and we're just going to go to how you would train this. So I have this data set called as GSM 8K train DeepSeek that contains all the stuff that the model should predict. And this is, again, obtained from like another model, right? So, and I'm gonna go here. I'm gonna say create new repository, add repository name, description, and I've already created a repository here. It's called Turbo, and I'm going to start a training job, right? So I'm gonna say new adapter version. For this, I'm gonna say I'm going to use GSM 8K train, right? So I've selected the data set. I'm going to select the language model, say Quen. Right, I have selected, and then all I have to do is click Turbo LoRa. This will train the model. This will train the turbos for me, right? So instruction fine tuning is correct. what is the rank of the LoRa's that I want to use, then which target models do I want to target. For now, let's just keep this. And then learning rate, blah, blah, blah. And then you just hit train, right? So this should start training the model. It'll get queued. It might take a few seconds, but believe me that it'll go into training and it'll start training the model. So we'll let the model train. So as Will said earlier, we are because we are really excited about reasoning models, uh, and we want to bring this to everyone, not just be restricted to a few labs. We have reinforcement fine tuning that's becoming available in our product soon. So do check it out. Here is a QR code to register for early access, and also for the next upcoming webinar where we'll be talking about GRPO, right? And reinforcement fine tuning is a really great case if you don't have a lot of label data. We have run a lot of experiments and we have found that even with uh, even with 10 samples in your data set, you can get pretty good accuracies, right? But in order for reinforcement fine tuning to work, you need something else, which is you need to have something called as reward functions. And reward functions are nothing but objective checks that you apply over the output of an LLM to tell you whether they are correct or not. Let's say you are doing math, right? The GSM 8K example. You can just check if the output returned by the model contains the correct answer or not, right? And yeah, you can, yeah, this is sufficient. And another thing that you can, another heuristic that you can apply to check whether your use case is a great fit for RFT, reinforcement fine tuning, is to see if instead of just asking for the answer, if asking the model to produce its thinking helps the model. This is called as chain of thought, right? So chain of thought versus few shot or non-few shot prompting, which is better? If chain of thought is better, then most likely RFT would be a good fit here. So, well, that's it. I'm going to stop here. And if you have any questions, if you have anything, yeah, let me know.
Yeah, thanks, Ajinkyo. We really want to open this up and see, who has questions, who's been experimenting with reasoning models, and maybe if people have other, techniques of getting around their speed. So again, we have the chat further below, and we have the Q&A tab also. Um, so I see a couple of questions coming in on the Q&A tab, which it's a lot easier to keep track of things in the Q&A tab, by the way. Um, Jinky, if you open that up, I'll read
Mhm.
this out for the audience. But are transformer blocks for multi-token prediction with, for example, DeepSeek models available at Hugging Face, or did you train your own?
Wait, let me understand. So transformer blocks for multi-token prediction. Oh, okay. Do you mean do you mean is the code for using those adapters available on Hugging Face or okay? So some of these adapters not for this particular task are available publicly. The DeepSeek adapter is not available publicly, right? And we train our own adapters, yes. And these are not open source implementations of there are other implementations of speculative decoding. This is what multi-token prediction is, that are available open source, but this is a much faster, much leaner implementation that we have in house. Okay, so the next question is, have you tried applying RFT to any vision models, especially vision language models? That's a great use case. I have some use cases in mind that I want to try out as soon as some of the stuff that we have been working on with RFT is over. But right until now, no, we haven't tried any vision and language models. That's a great idea, by the way.
Love it. Um, let's see. Another question, talking about DeepSeek architectures. How does
Mhm.
LoRa compare to DeepSeek's multi-head latent attention?
Yeah, so the models that we have tried, that we have fine-tuned, are not DeepSeek architectures. We have tried Quen models, which don't have DeepSeek architectures. Now, multi-head latent attention is mostly restricted to the attention block and the projection layers, right? So and there is a projection layer that goes from keys and values. Yeah. Suffice it to say that we don't have DeepSeek, but once we have DeepSeek, yes, we can target the projection layers in the MLA with LoRa's.
So, thank you. Also in chat, I just put another link to the upcoming webinar. The QR code is right here also. But next week we are excited to share our GRPO SDK. So this is available in the platform today. We are pretty confident that this is the first SDK available for doing GRPO fine-tuning. So you can actually create your own reward functions and start training models with RFT in Predibase now using the SDK. Very curious if that's something that, other folks are kind of exploring, if people feel like they have interesting use cases where RFT could be a good fit. See those 3 points that Ajinkya put up right there, to help identify if you might have a good use case. All right, I'm going to go back to some of the questions now. Let's see. As a follow-up, on top of your head, do you think applying RFT to vision models would be straightforward to implement, or do you think it would need some addition or modification to the existing models or systems?
So the way RFT works, it doesn't do anything inside the model. It's a standard LoRa adapter that you add on top of the model. So the only complexity for going from normal text-only LLMs to vision language models would be that you need to have support for the vision model in your system, and we already have that. Right? So, and we already support training with LoRa's. The only thing that we have to do is think about how the training actually happens. Like, what is the input? What is the, like, yeah, how do you check the output, right? That's how do you calculate the rewards. That's the only thing that needs to change. And once that is set, all you need to do is run the thing. So the change that happens in RFT versus SFT is on the loss function side, nothing in the architecture or the internal model side. So Arnav is asking, what kind of reasoning tasks do you think will benefit the most with Turbo LoRa training on models like DeepSeek? So yeah, any reasoning tasks where we see a lot of repetition of tokens, or there is like a structured. For instance, you're trying to do analysis over a table, or trying to do analysis over an HTML or some code where there is some structure, and if you had access to, let's say you're outputting Python, right? And the first token that comes is D, then there is a chance that you're trying to write code for a definition of a function, and then it would be DEF. So the next three tokens, right? So stuff like this. And let's say you have end of the function syntax, then you should output colon and stuff like this, right? So these are the tasks where there is some structure and there is some repetition, are the tasks where Turbo really shines for reasoning models. And Sanjay is asking, we have a use case where we have a lot of unlabeled data for span extraction type of problems from the text. How would reward functions work in the case of RFT for verifying the output of such problems, since spans can contain any sequence of tokens? Uh, the problem statement, I'm not like fully familiar with span extraction, but I'm assuming that it is some sort of text extraction, that you have a huge text, and then you need to copy a portion or relevant portion based on what the user has asked from the input to the output, right? And if this is the case, then you could create a synthetic data set, right, where you know what you can create questions for which you know what the span should output. And yes, you're right, the number of tokens in the span can change. But all you need to check is whether the span that the model produces is same or approximately similar to the span that is present in the input. You could use string comparison algorithms where they provide how many characters are off between what the model outputs and the counter output. So that would be a nice continuous reward function, where if just one token is off, then you don't get a huge penalty for the reward. But If a lot of tokens are off, then the penalty is higher.
Awesome. And Sanjay, feel free. We're happy to chat more about that use case and see if we might be able to offer any guidance on it. I'll send you a message or I'll put my email address in the chat for everybody. But yeah, please feel free to reach out and we're happy to explore that use case with you a little bit. All
Yeah.
right.
So I see another question in the chat. That's Can you briefly explain the training data set? So the data set that we use is GSM 8K. It consists of math questions, and it comes like and the we have the answer to those questions, right? So that's it. It's a prompt that asks a math question, and the answer is present in the data set. So you take this prompt, the question, you forward it through a model, and it generates a bunch of tokens that consists of two parts. The first part is the think tokens where the model is reasoning, and the other portion is the actual answer, right? So inside the answer, you enforce the model to put the actual answer in a particular format, and you train with two rewards: whether the model put the answer in the correct format in the output, and the second is whether the actual answer matches the actual answer or not, the answer that the model provided.
So, um, we do have more time for a few more questions if folks are either curious about RFT, the GRPO SDK, any of this Turbo LoRA, kind of accelerating these models, or how to try that yourself on a use case you have in mind. Um, and as a reminder, please do consider checking out the webinar next week. We're excited to kind of show off how this SDK is going to work and kind of give you that early preview of what our reinforcement fine-tuning capability is going to look like. Yeah, let me put the link in chat again. Um, yep, here's the link for next week's webinar. Okay, another question. How does the model performance with speculative decoding compare to the model performance without? Great question. Love it.
Yeah. So the model performance doesn't change at all, and the idea is that when you're doing this sort of turbo training, we are not trying to change the output of the model. We are just trying to predict the next tokens, right? And let's say you try to predict something and it is not correct, right? There is a verification step that happens that makes sure that whatever you predicted matches with what the model would have predicted normally, right? So there is a sort of randomness in this whole process, that if the prediction is correct, then it gets it then there is a speed up. If it is not correct, then you don't see the speed up, right? So the model performance doesn't change, you only speed it up.
Yeah, and that's really, I mean, one of the, kind of superpowers of Turbo LoRa is you get all those speed benefits without any impact on quality, kind of overcoming some of those more historical trade-offs between speed and quality.
Yeah. And it's also very easy, as you saw. Like, all you need is a data set that you can generate very easily by querying a model. Once you have the data set, you just throw it in the site and it just works. You're going to get out a turbo that just makes things faster. So again, there is one more question. So how often do you fall back on the non-speculated tokens? So again, this is data set dependent, right? So when I say we get a speed up of 2x, it means that for every token that you have, you are able to at least predict the next one token accurately on average, right? Uh, it's not every token that it's not for every token. For some tokens, you'll be able to predict the next three tokens. For some tokens, the next predicted tokens won't make sense, right? And so but on average, you are able to predict two tokens instead of one token, and that's how you get like a 2x speed up. This is data set dependent. If you have a different data set, the speed up that you see could be 1.3, 1.2, or it could also be 3x speed up.
Cool. Well, again, thank you everyone for so much for coming up. Thank you, Ajinkya, for walking through all of this work. You're the author and the mastermind behind a lot of this work and all the data that folks saw. So thank you for showing it off. And again, folks, next week, really excited to have a follow-up webinar about the GRPO SDK. Hope to see some of you there. And really excited for some of our RFT offerings that we're building that are around the corner. So without further ado, thank you everybody for showing up today and hope to see more of you next week. Appreciate it. Take care, folks.
Thank you.